Okay, on number 1, this is like a classic ACT problem here. You have a ladder leaning up against the building. I'm not going to bother reading it. So, especially on one strategy about the ACT is there are some questions, not a lot, but you can tell what this question wants right away without having to read through all the words here. So all they're doing is just looking for this leg of this right triangle, and everybody should know here that we're just going to use the Pythagorean theorem here. So let's notice here that the hypotenuse is given. So when we use the Pythagorean theorem, we should know here that the hypotenuse is the c squared part. So what's missing is one of the legs, which you could call A or B. So I'm going to say h squared plus b squared equals 10 squared. Now, when we square these, we get those numbers. And now, it's just a quadratic equation here that we can solve by the square root method. So we get b squared equals 36, and then we can take the square root of both sides, and so that'll give us plus or minus 6. Now, because this is just a positive triangle, it would just be positive 6. I don't think anybody would really think to even put plus or minus on a question like this anyway. Okay, on number 2, it says, what is the length in inches of a diagonal rectangle whose dimensions are 16 inches by 30 inches? So let's draw us a rectangle here. So this will be my 16 inches, and this will be my 30 inches. Now, we should all know what a diagonal is. So a diagonal runs from one vertex to an opposite vertex. So that would be a diagonal. And so clearly, since a rectangle forms 4 right angles here, we can just use the Pythagorean theorem. So we'll just say, we're missing the hypotenuse this time, so we would say 16 squared plus 30 squared equals c squared. So this would be 256 plus 900 equals c squared. And then 256 and 900 is 1156. Notice that's one of the choices there. So that is a distractor. We should know that we should take the square root on both sides. Now, the square root of 1156 get my calculator for that. Is 34. So this would be plus or minus 34. Of course, since it's in a triangle, it would best be positive 34. Okay, on number 3, we have another rectangle. So rectangle ABCD. If you didn't know this from geometry, when you label your quadrilaterals, you're supposed to do so in a clockwise order. Now, this has a diagonal of 6 units. Okay, so my diagonal is 6. And one side measures 3. And now we're asked, what is the perimeter in units of the rectangle? So in this case, we should know that this side of the rectangle would also be 3. But what's missing, obviously, is this side and this side. So to find the perimeter, we sum up the sides. Well, we're missing the bottom and the top side. Well, again, since a rectangle forms right angles, and the diagonal there goes through it would form a right triangle, then we can just use the Pythagorean theorem down here. I'm just going to call this A to find that side. So we can say a squared plus 3 squared equals 6 squared. So we'll get a squared plus 9 equals 36. Okay, so we're going to subtract 9 from both sides here. So we'll get a squared equals, and then 36 minus 9 would be 27. Okay, now let's take the square root of both sides. That's not a perfect square, but we can break that down with 9 and 3. So this would be plus or minus 3 squared root of 3. Now, since it's obviously just a regular rectangle here, it would be just a positive 3 squared root of 3. So this distance up here would be the same since it's a rectangle. Now, all we have to do to get the perimeter is just sum all the sides. So when we do the perimeter, we wouldn't count the diagonal. So all the sides here, so the left and the right side is a 3 and a 3, and then the top and the bottom is 3 square roots of 3 plus 3 square roots of 3. Now, the 3 and the 3 there would give me 6. Now, when we add and subtract radicals, we leave the radicand alone there. And before I can add or subtract radicals, the radicand has to be the same. So 3 square root of 3 plus 3 square root of 3 would be 6 square root of 3. So our perimeter there is 6 plus 6 square roots of 3. Now, number 4, we have this diagram here. It says C and O are the centers of the bases of a right circular cylinder in the figure. So we have a cylinder, and the base, or the top and the bottom, are considered to be circles. Now, the height of the cylinder is 6 inches, and XY is 4 inches. So let's label all this information here. So we've got the height is 6 inches. Okay? And what I'm going to do, I have an intuition about most stuff like this, is I'm going to go ahead and put that height there too, because when I put a height, I make a right angle. And so somewhere, if I want to, I can use a right triangle and the Pythagorean theorem. Now let's see what else they told me here. I got XY is 4 inches, so XY would be the diameter, and so I'm going to use this instead. Now I may use that 4 inches, but each radii here would just be 2 inches. Okay. Now here again, let's see what we're looking for. Here's the question down here. It says, which of these is in inches is closest to the perimeter of triangle XYO? So triangle XYO here, we're looking for the perimeter of this triangle. Now, so I know I have one side. Let me redraw this triangle over here. Clarity here. So I have one triangle, or one side of the triangle is 4. Now what we need, though, is the other two sides of the triangle. Now, you can kind of see, probably I just had an intuition that I knew I would have to probably draw the height right here into the triangle in order to find that length right there. So if you'll notice, we'll highlight it in green here. We've got a right triangle, and that missing side of that triangle that we need for the perimeter is the hypotenuse. So we can just say they're 2 squared plus 6 squared equals c squared. So that'll be 4 plus 36 would be c squared. So that'll be 40. And then we're going to take the square root of both sides. The square root of 40, we say 4 times 10. So it'll be plus or minus 2 square roots of 10. Now, I'm going to notice this. My answers, unlike the last question, are not in radical form. So probably what I want right here, instead of 2 square roots of 10, what we really need is just the decimal approximation for that. So on my calculator here, I can type the square root of 40, and I'm noticing that my answers are to 2 decimal places. So I'm going to write that to 2 decimal places, 6.32. Now, you can tell here, this is probably an isosceles triangle, because the other triangle in the picture, since I've divided it up with 2 triangles with my height, is identical. So it's also...
Excuse me, teachers and guidance counselors.
So now we have this side is also 6.32 there. So now, all we have to do is just sum up all 3 sides of my triangle for the perimeter. So I'm just going to type in my calculator here, 6.32 plus 6.32 plus 4, and that's about 16.64. Now, I don't see 16.64, but I see this, and probably what happened was that when I rounded off to 2 decimal places, I've got a little bit of error with my rounding right there. But that's probably the answer there. Okay, on number 5, we have triangle XYZ. Notice they don't give me a picture, so I'm going to start drawing while I'm reading. Triangle XYZ, and we know that XY is congruent to XZ. So XY is congruent to XZ. So it's just screaming here, hey, I'm an isosceles triangle. Now, it says the measure of angle Y is 34 degrees. what is the measure of angle X? So what we have to use here, this is one of the things that we talked about yesterday. So we have an isosceles triangle, two sides are the same, but two angles are also the same. So the two angles that would be the same here would be Y and Z. Now, even though I'm not looking for Z, I should know that Z would also be 34 degrees. And now I can just sum my angles up to 180. So we got 34 and 34 is 68. And then 180 minus 68 here would just be 92. I probably did that wrong. Let me just put it in my calculator. Let's read that up. 112. That makes sense. Okay, the next one here we have the measure of the interior angles of a trapezoid are in the ratio of 3, 4, 5 to 6. What is the measure of the largest interior angle? So I'm just going to draw myself here a trapezoid. Now we talked about this one yesterday. We have the ratio of the angles. That doesn't mean that one angle is 3 and one angle is 4 and one is 5 and one is 6. But instead, what it means is each angle is 3 times, or that angle is 3 times some value. This one is 4 times some value. This one's 5 times some value. And this one is 6 times some value. Now, so since we know this, and we should note here, if we have a quadrilateral, the sum of the angles in the measure of a quadrilateral should sum to 360. So these angles, 3x, 4x, 5x, and 6x, should add up to be 360. Now, if I sum those angles up, 3 and 4 is 7, and 5 is 12, and that's 18. So we'll get 18x equals 360. Now we'll divide by 18, and we'll get x here to be 20. So now my largest angle here would be the 6x, and if x is 20 here, 6 times 20 would be 120. Okay, that's a very similar question here. It says, shown below, a circular dartboard has 4 sectors, red, blue, white, and green, whose areas are in the ratio of 1 to 2 to 3 to 4, respectively. Okay, so respectively here means that the 1 is for the red, so we should know from the last problem, we're just going to call that one 1x. And then the 2 would be for the white. You can kind of tell by the measures or how big each little sector is. By the way, what's a term that I use sometimes? A sector is, this will be an example of a sector, sort of like a piece of pie. That's what a sector is. Now, let's see, the green would be, let's see, the blue would be 3x, and then the green would be 4x. Now let's see what we're going to do with this. It says, Brad will throw 1 dart at the dartboard. It will hit the dartboard at a random point contained in one of the sectors. What is the probability that the sector of the dart hits is not the blue sector? Okay, so what we're going to do is we're going to assign a certain area by using the sum of the degrees in a circle to see, how much of the circle in terms of degrees are in each area here. And then we'll be able to find the probability. Now, more specifically here, well, let's just find all of them. There's no big deal. So we're going to sum these up. So we should know that the sum of the degrees in a circle is 360. So if we sum these up, you get 3 and 4 is 7, and 1 is 8, and 2 would be 10. So we would get 10x equals 360. So now we would just get x here to be 36. So what we can do is divide those angles up for each of those sectors by using our ratios that we're given. So the blue area, that's really what all I really need to do. And I recall it was 3x. So 3 times 36 here is 108 degrees. Okay, so we get the measure of this sector. The angle for the measure of that sector is 180 degrees. Now we're looking for the probability that we don't hit the blue. Well, let's find the probability that we do hit the blue. So the probability here, remember probability we do are possibilities over all the possibilities, so that would be a part to total. So that would be 108 divided by 360. Now, so I get right here that this would be 0.3. Now, that would be the probability that I did hit the blue. So the probability that I didn't hit the blue would be that I would hit anything else. So we have 0.3 for the blue, then everything else would be 0.7, because the 1 is our total probability. So 0.7 here is the same thing as 7/10. Okay, on number 8, it says in this figure below, the circle with a center O has a radius of 7 inches. So let's put this in here. And the measure of arc AB is 80 degrees. So we want to know what is the measure of angle BAO. And so they have that question mark marking that angle for me. So what I'm going to do here is I'm going to add a little bit to the picture. So a lot of circular pictures like this, when you're finding angles, you're going to have to add in radii. So I'm going to add a radius right there. Now what I'm going to use is that every radii of this circle are the same. So this radius is also 7 inches. Now, so how does that help me find my angle? We're going to get there. So let's also notice that the measure of an arc with its central angle, this is called a central angle right there, is the same thing. So that angle would be 80 degrees. Now, let's notice that when I had this triangle right here, I've got two sides are the same. This side and this side are the same. So that makes it an isosceles triangle. So since that's an isosceles triangle, these two angles will be congruent there because they would be my base angles. So we don't know what each of them is though, so let's start. We should know that there's 180 degrees in the circle, and we're going to take out that 80. Now between the two angles that are left, it'll be 100 degrees. And so if they're the same, one would have to be 50, and then the one that I'm looking for right there would also be 50. Okay, on number 9, it says a square has the same perimeter as a regular hexagon, and it gives you a hint here that that's a six-sided polygon with all sides congruent and all interior angles are congruent. We mentioned that probably yesterday. If one side of the square is 108 centimeters, how many centimeters long is one side of the hexagon? So this is something I definitely want to draw a picture to kind of help me figure out. So I have a square, and then I have a hexagon. I have a little bit of trouble drawing the hexagon. It's not that big of a deal. You just draw like that, and you just draw the same thing on the bottom. Here's your hexagon. Now, let me read back through it again here. So they have the same perimeter. Now it says one side of the square is 108 centimeters. Okay. Now let's deal with the perimeter.
Miss Jacobs, report to.
Now my hexagon should have the same perimeter. So what we're going to do quickly here is just find the perimeter of that square. So each side of that square would measure 128 centimeters. So I'm just going to say 108 times 4. And I get the area of my square here is 432 centimeters. Now, remember, my hexagon, it says in my problem, that this should also have 432 centimeters. Now, the difference, obviously, is the hexagon has 6 sides. So, and if it's a regular hexagon, that means every side...
And Jerica Gray, report to the main office to check out. And Jerica...
So we just take here, since they're all the same, and we're going to do 432 divided by 6. So let's do this quicker than I can probably punch in my calculator. And we'll see that that's 72. So each side of my hexagon will measure 72 centimeters. Okay, on number 10, we've got a boat that departs Port Isabel, Texas, traveling to an oil rig. The oil rig is located 9 miles east and 12 miles north of the boat's departure point. About how many miles is the oil rig from the departure point? So let me read back through this again. Basically, probably what this is just drawing a right triangle. So we're 9 miles east. Okay, so I'm going to draw me a little compass here. Never eat sour worms. All right, so we're going to go, let's see, what did it say? 9 miles east. Here we go. 9 miles east. And then we're going to go 12 miles north. 12 miles north. Now, we want to know how many miles is the oil rig from the departure point. So that would be the distance from where we started to where we would currently be. So you can tell here, if I went due north, that's going to be a right angle, and that's going to be a right triangle. So that's just another Pythagorean theorem question there. So we can just say 9 squared plus 12 squared equals c squared. So that would be 81 and 144 there. 81 and 144 is 225. Okay, and then we're going to take the square root of both sides there. So we'll get plus or minus 15. So it's just 15 since we're in the first quadrant there, everything's positive. All right, number 11 says, what is the degree measure of the acute angle formed by the hands of a 12-hour clock that reads exactly 1 o'clock? So let's draw this picture. So this one's 12, 3, 6, 9, 1, 2, and we go all the way back to 12. This is all I really need. So what I'm looking for is the measure of that angle. Okay, so here's what we're going to use. We have a clock, and this is, obviously circular. Okay, and if I go all the way around that clock, that would be 360 degrees. Now, however, I'm only going this much. So that's only 1/12 there. That's one way to look at that. Okay. Now here's another way. We have 360 degrees in my clock, and my clock is divided up into 12 hours. Okay, we'll say 360 divided by 12 here. And so that would be 30 degrees. Okay. So that means each hour that passes here, the clock hand just moves 30 degrees. Now, since it's just on 1, it would just be 30 degrees. So, for instance, if it was on 2, it would be 60 degrees. If it was on 4, it would be 120 degrees. Okay, every hour that you're moving is 30 degrees there. Now, number 12, this is really a classic problem on the ACT. Usually you get some version like this one or some of these next ones here that are all really, really similar here. Okay? There's always a question, something like this. In one case, I believe last year, and they had it in 3 dimensions, and it was a sphere inside of a cube, but they all have the same idea. So this says that the circle has a radius of 1 inch, and it's inscribed in a square. What is the area of the shaded region in square inches? So these shaded region problems, all they are is basically just using some subtraction here. Okay? So what I'm really going to do to find these shaded regions is just take the square and subtract the circle to find the shaded area. So what I need to do, though, is I have to find those areas. So on my square, notice that they didn't give me any dimensions to my square, so I have to figure this out. So what I'm going to do to figure out a side of the square is use this 1 inch radius. So if that radius is 1 inch, if I drew a diameter through that circle, that would give me the length of one of the sides of the square. And if the radius is 1 here, that means the diameter or the sides of the square are each going to be 2 inches. Okay. Now for the area of a square, it's just like with a rectangle. You would do length times width. Now if we don't know that formula, remember that formula can be found in your ACT program. So this one's going to be 4 square inches. Okay, now let's find the area of my circle. Now here again, you probably forgot about the area of a circle, but the area of a circle, and find also in that program, is pi r squared. Now notice that most of my answers are in terms of pi. Okay, so I really don't have to use 3.14. All I have to do is take the radius squared. So this would be pi times 1 squared. Recall the radius was 1 right there. And so that would just be pi. So we get 4 minus pi there would give me the area of that shaded region. So that answer was C. Okay, on number 13, basically the same problem. It says the square below has an area of 64 square centimeters. Now that's not the perimeter, but it's the area. Okay, so let me write this down here. This is the area, use some notation, of my square is 64. Now, the circle inscribed in the square is tangent to the points A, B, C, and D. Now, tangent to means that this curve only touches that line at one point. And that's what you get when you inscribe something. You get the tangent idea. Now, it says, what is the area in square centimeters of the
Teachers,
circle?
pardon the interruption. I need Aisha.
So let's use this area of the square to figure out the circle. Now, recall the way that we get an area of a square is we just say the length times the width. Now the thing is, the length and the width of a square should be the same number. So what number would I multiply by itself to get 64? Or basically the square root of 64. So that means, get back there, that each side of the square would be 8 whatever. I forgot the units. I'm not worried about units on the ACT, by the way. Now, so if we get 8 here, if we measured across the circle right here, the diameter of the circle is also going to be 8 whatevers. Now, what we need for the area of the circle is pi r squared, just like in my last problem. We need the radius. So if the diameter is 8, then my radius is going to be 4. So this would be pi times 4 squared. And 4 squared is 16. So that would just be 16 pi there. Okay, so you always get this problem where you have a circle inside of a square, or sometimes a square inside of a circle every once in a while. All right, same thing right here. Okay, almost identical to number 12. It says a circle with a diameter of 8 inches is inscribed in a square shown below. What is the area in square inches of the shaded region? This is a little bit different than that last one. We've got the shaded region we're trying to find the area of. But it's basically the same thing here. I'm just going to take the square and I'm going to minus the circle. Now, what that would find me, though, is that would find me all 4 of these. Okay? So that would be all 4 of these corners right here. And so if all I'm looking for is one of the corners, then we would just take that and divide it by 4. And that would just be one of them. Now, let's find our areas here. So if this diameter all the way across is 8, that means each side of my square is 8. So the area would be 64. Now, let's find the area of my circle. Now, the radius of my circle would be 4, and the area of a circle, recall just a minute ago, is pi r squared, so that would be pi times 16, so this would be 16 pi. So the area of those 4 corners would be 64 minus 16 pi, but then if I only want one of them, then all I have to do is just take all that and just divide by 4. So we can reduce out by a 4 right here. 64 divided by 4 is 16, and then 16 divided by 16 pi divided by 4 would be 4 pi. So we get 16 minus 4 pi, which was h there. Okay, on number 15, very similar problem. We have an 8-foot square sheet of 10 in which 4 identical circles are cut, as is shown below. Each circle is tangent to 2 other circles and tangent to 2 edges of the square. So what that means, again, is when we're tangent, we're only touching at one point. So in other words, they are not, anything here is not overlapping. Now, it says, what is the approximate area in square feet of the remaining 10 as indicated by the shaded region? So it's another shaded region problem. Now, this is a little bit backwards from earlier. So what I'm going to do, find the shaded region, is find the area of the square, and I'm going to subtract the area of those four circles. Now, you should realize those circles are going to be identical. So all I really have to do is find the area of one of them. Now, the area of the square is pretty simple to see, that would just be 8 times 8, and so that's 64. Now, let's figure out the area of the circles, though. Okay, now, just remember that the distance across the square was 8. So the distance across 2 of these circles now would be 8. So that would break each circle into diameters of 4. And if the diameters were 4, then the radii would just be 2. Okay, so let's just find the area of one of the circles, and then we'll just multiply it by 4 since there's 4 of them. So the area of the circle there, here we go again, pi r squared. So pi times 2 squared would be 4. So each circle here would be 4 pi. So if each of the circles are 4 pi, all of them together here would be 16 pi. Now this time, you'll notice that the ACT doesn't always give the answers in terms of pi. They're in decimals, so really all I have to do is just type in my calculator using 3.14 for pi, or the pi button. Now, since you're supposed to be able to do the ACT without a calculator, you don't have to use the pi button. I'm just going to say 64 minus 16 times 3.14, and we get 13.76, and that's probably the closest one to it there. Okay, on number 16, the question is, what is the sum of the interior angles of this figure? So notice it is not a regular polygon, so I'm going to use my strategy here. What I'm going to do is divide this into triangles. And so I see a little shortcut here that I can do is I can just extend this line right here, and then I'll break, how can I do this? That'll be parallel with that one. Here we go. And this, notice I have like sort of a, it's not exactly a trapezoid, but that's sort of a trapezoid. What I'll do is break it up into 2 circles, two triangles, excuse me. So what I have now is I have 1, 2, 3 triangles. So remember the idea, when you want to sum the interior angles of some sort of polygon, is you want to break that up into triangles. So since I have 3 triangles here, I can just say 3 times 180. 3 times 180 is 540. Okay, you've also could have figured out that that was a 5-sided figure, so it would be a pentagon. It doesn't look like normally a pentagon that we get. You can also do that formula there, n minus 2 times 180. Okay, now this one's very similar. It says in a regular pentagon, all 5 interior angles are congruent. What is the measure of each of the interior angles of a regular pentagon? Now, this is actually the example that we did the other day here. So if I have a pentagon, all right, first what we want to do is find the sum of the angles. So again, we can divide this up into triangles, and what we'll get is 3 triangles, just like the last problem. So the sum of the angles is 540 degrees. Now, since it's a pentagon, it's going to have 5 sides and 5 angles that are all the same. So we'll just take that and divide it by 5. 540 divided by 5 there is 108. Okay, on number 18, this is a little bit more complicated here. It says 2 interior angles of an octagon sum up to 480. What is the average measure in degrees of each of the remaining angles in the figure? Now let's draw an octagon. It's kind of hard to draw. Whereas octagon is a stop sign. Okay, so now what I'm going to do is I'm going to take one vertex right there, and I'm going to see how many triangles that I have so I can get the sum of the interior angles. So let's draw it to each one of the vertices. Now I can't draw it to that one, but we can draw it to this one, and then this one, and this one, and this one, and this one. So if I count my triangles here, I'm going to have 1, 2, 3, 4, 5, 6 triangles. Okay? Or, you could use this formula, n minus 2, and then times 180, because each triangle has 180 degrees. So if you had an octagon, that's 8 sides, you would say 8 minus 2 is 6. So you get 6 times 180 is 1080. Okay. Now, this one's not a regular one, so we can't divide it by 8, but it says that 2 of the interior angles sum up to be 480. So I'm going to take those 2 angles out. So 1080 minus 480 is 600. Now, since I've taken the 2 angles out, okay, so I've subtracted the 2 angles, then that means the other 6 angles have to have a sum of 600. That means that they would have to average around 100 degrees apiece there. Okay, on number 19, we have triangle ABC is an equilateral triangle with an area of 32. Triangle DEF is an isosceles triangle.
John Rigger, report to the main office.
And the other triangle has an area of 64. So which of the following represents the ratio of the sum of the interior angles in triangle ABC to the sum of the interior angles of DEF? So 2 triangles here, ABC. This is a trick question, by the way. And we have triangle DEF. It told me about the areas. So this one had an area of 32. This one had an area of 64. So I'm going to say square, whatever. Okay, this area. Now, it says, what is the sum, what is the ratio of the sum of the interior angles? So, hey, guess what? Area has nothing to do with angles here. The sum of the interior angles of this triangle is 180. And the sum of the interior angles of the other triangle is also 180. That had nothing to do with the problem. So 180 to 180 is 1 to 1. Trick question, number 20. All right, we have 5 congruent circles shown in the diagram below, have their centers lying on the same diameter of the larger circle. Each circle is tangent to 2 other circles. That means that they're only touching at one point. If the area of each small circle is 4 pi squared units, what is the area in square units of the larger circle? So ultimately what we need is we need the radius, or the diameter, of the big circle. Now, notice it didn't really tell me the radius or the diameter of the little circles. All it told me is that each of these little identical circles here have an area of 4 pi. Okay, so let's just note that the area of that little one there is 4 pi. So what I really need to know here is just to take the area and work backwards to find out what the radius of each little circle would be. So the area is 4 pi, and we know that the area is equal to pi times the radius squared. So if we know that the area is 4 pi, we'll get 4 pi equals pi r squared. Now we just need to solve for the r. So we would get rid of the pi. So that's just going to give me 4. Most people could kind of just use common sense to figure this out. But that's just going to mean that the radius is 2. Now, not on the big circle, but on the little circles. So if each radii was 2 on each circle, that means each diameter would be 4. So that one's 4, that one's 4, and this one's 4, and this one's 4, and surprise, this one's 3. No, it's 4. Now, so here we go. We got 4, 4, 4, 4, and 4 is 20. And so that means the radius of my big old circle here is 10. Now, I can find the area of my big circle because I know the radius is 10. So the radius is pi times the radius squared. So it'll be pi times 10 squared. 10 squared is 100, so that's 100 pi. Okay, on number 21, it says the circle in the following figure has a center C and a radius of 5. Okay, now it didn't tell me which radius is 5. Well, guess what? All radii are the same. So every radius is 5. It says, what is the length of chord EF? Now notice, this is a right triangle right here. EF is what's called a chord, but it is also the hypotenuse of that triangle. So we can just use the Pythagorean theorem here and say 5 squared plus 5 squared equals c squared. So that's 5.
Ashley Dieter, report to the main office to check out. Ashley Dieter, report to the main office to check out.
Okay, 25 and 25 is 50. And then we would just take the square root of both sides. Now with 50, just say 25 times 2. So that will be 5 square roots of 2. Technically, plus or minus 5 square roots of 2, but only the positive version. So it was B. Okay, on number 22, we have to find the perimeter. Okay, so I don't have to read all that. I can just read the question. Got to find the perimeter. So I've got to add all the sides together. Now let's notice, though, that this side is missing. Shame on them for not telling me that side. Now we can figure this side out. So I'm going to notice here that it's almost a rectangle. It's got a rectangle that just like grew a nose or something. So what I'm going to do is just going to section this little piece off right here. Now we should notice that this distance here, I'm forming a rectangle, so it should be the same as that. So that's going to be 10 feet. Okay. So now all I have to do is find this distance. Okay. And if we didn't know how to find that distance, we could at least add what we had and then just kind of say, well, it's got to be a little bit more than what I've got right here. Now, let's find this other distance. So what I'm going to notice here is when I section that off, I formed a right triangle. And if you notice here, we have this distance is 6 feet. Okay, so all that is 6 feet. And then this part of it is 3 feet. So that means that this distance on this triangle right here would be 3 feet. And what I can do there is use the Pythagorean theorem to find that missing side. So we can say 3 squared plus b squared equals 5 squared. So we get 9 plus b squared is 25. We'll subtract 9, which is 16. So this side right there is 4. So now, all I got to do is go all the way around the triangle, or whatever this is, okay, a rectangle with a nose, and add all the pieces together. Now I'm going to start with the 4, the one that I found. So I've got 4, 10, 6, 10, 3, and 5. So let's see, that would be 14, 20, 33, 38. Okay, on number 23, and this one you didn't have a multiple choice one, so you just had to leave your answer sheet blank on that. I probably should have come up with some. Now, really what I wanted you guys to do in this problem is if you watch the video on how to use the system solver on the graphing calculator, okay, is to use it. All right, so we can just, don't know why I did that. Stop it. It won't stay the same. Every time I click on it, it changes size. All right, here we go. So we can go to, where was it? Systems of equations, the third menu. Okay, and when it says how many, that's like how many equations. I have 2. Okay, and now all I have to do is type in the coefficients and the constants on the equation. Now notice they would have to be in this format. Okay, so you'll see one next here. But if it's not in a standard form, you have to rearrange your equations in standard form. So the A is 3, the B is 7, and the constant is 15. Now equation 2, the A is 5, the B is 2, and the C is -4. So there we go. I don't know why it puts the answer twice. Okay. Maybe, yeah, 2 equations, I guess so. All right, so there's my answer there. X is -2, Y is 3. Okay, now on number 24, now you'd have to do a little bit of tweaking on this one to figure it out. Okay, but I think you guys can figure it out here. All right, so what will we have to do to be able to like throw it into the program really quick? First equation's not in standard form. What do we need to do? Right. And so that's just going to make it be 27. Okay. So let's just use that now. Okay. And so now I can just throw it in my calculator. Now the question is what's y? So let's keep that in mind. All right. So here we go. Systems. It's 3. How many? 2. Okay, now let's just put in our A, B, and C. So we got 1, 2, and 30. 1, 2, 30, and then 2, 1, and 27. 2, 1, 27. Okay, so we get 8, 11. Now this one's only asking, again, for the y value. So that would just be 11, which is C. Okay, from 25. Now this one, we can't use the program. I did one like this yesterday. Okay, it says, for what value of A would the following system have an infinite number of solutions? So what happens on the infinite number ones, what should happen is that they should all cancel out. Now to get that to happen, I have to change them a little bit. So I could eliminate the X or the Y. In either case, what would you multiply that top equation by to get it to eliminate? Right, -3. Okay, let's just multiply the top equation by -3. So I'll get -6x plus 3y equals -24. Okay, now let's just copy that other one underneath. And so you'll notice, just like with an infinite system, that these should all cancel out. Okay, so that goes away, that goes away. Now, what value of A do we need right there to make that go away? A 6, because we need a 24 there, right? Okay, so that would just be 6. Easy question if you know the direction ahead on those. And they usually ask these are some of the questions that actually come toward the end of the ACT test that are actually considered hard. All right, now this one we've got, looks like a parallelogram. Okay, it is, parallelogram ABCD. So we want to know what's the area in square units. Okay, so now this is probably something that y'all don't know. You probably don't know what the area of a parallelogram is. Okay, that's what that calculator program is there to help you with. Okay, but the area of a parallelogram is the base times the height. Okay, so that's all we have to figure out. Now, it should be fairly easy to figure out what the base is. Okay, that's 2, and then this is 7. All right, so what would my base be, y'all? From 2 to 7, how far is that? 3, 5. Okay, okay, we need to count 1, 2. Get our fingers out. Okay. By the way, you can use fingers on the ACT. If you wear open-toed sandals, you can use your toes too. Okay. All right. Now I've got to find the height. Now the height is a little bit different here. Okay. So the height would be like the perpendicular distance from the x-axis. Okay. So the height would be like this. Okay. Kind of get that part. So really all you have to do is look along the y-axis. What would the height be? Going from here to here. How many units is that? 8. Okay. So base times height. 5 times 8 is 40. Okay. There again, that's where that program is really going to help you out. All right, 27. So this is a very popular problem on the ACT. You get it probably three-fourths of the time. You get something like this, where you have a triangle, and you've got a parallel side, or 2 triangles. A small triangle and then a larger triangle. And what happens when you have two of the sides that are parallel, that means that, that they're similar. Okay? So you have similar triangles that's ultimately going to solve this. Now, so the question is, what is the length of AB? Okay? So if you try the Pythagorean theorem, because it's the right triangle, the problem is you don't have the hypotenuse. So again, what you have to use is the idea that the triangles will be similar by the angle-angle postulate. Okay? Because if we have these two lines are parallel, that means these two angles are congruent, and of course these two angles are congruent. So the triangles are similar. So a lot of times the way I taught this in geometry is I would draw the two triangles separately. So we've got the big triangle, big right triangle, and then we have the smaller right triangle. Okay? And I can just use similar triangles to find this side right here. So I'm going to call that X. Now we got this side of the big triangle is 20. Now let's look at the other information that we were given. This side was 15, and then this side was 5. So we can just use a simple proportion here. So that 15 to 5 should be equal to 20 to X. So we cross multiply here, we get 15X equals 100, and then 100 divided by 15 is, I don't know, 100 divided by 15 is 6.6 repeating. Now, do y'all know which one of those is 6.6? Well, this one's the only one that's got 6, so that's kind of obvious. Okay? But 6 2/3 means 6.6 repeating. All right. That's it. Okay.
What about the 25?
Which one?
The 27.
27?
The 25 is the hypotenuse of 3. Okay, why would you not use that?
Because you didn't have the hypotenuse of this one. Okay? So if you would have had the hypotenuse of this one, then you could have used the Pythagorean theorem. Okay? Or if they didn't give you, for instance, if they wouldn't have given me the 20, or if they wouldn't have given me the 5, okay, and they gave me, and they gave me this one, then I could have used another proportion. Okay? All right, but you didn't need it.